So we've got two radio towers. We know they're 8 kilometers apart. We know they're both transmitting radio waves. And we know that they're both the same frequency, 3.75 times 10 to the fourth hertz. We also know they're out of phase with each other, that the waves from tower B are pi over 2 ahead of waves from tower A. And what does that mean? How would you describe the behavior of these radio towers if we want to say that one of them is pi over 2 ahead of the other?
What I understand is like phase constants are like the starting point. So I'm assuming that the wave coming from B is starting at a different time than A.
Yeah, you could think of it as sort of an offset in time. That these, if the phase constants were the same, then the waves, the sources would be in sync with each other. Like they both create a crest at the same time, both create a trough at the same time. They'd be synchronized. The fact that the phase constants are different means they're out of sync with each other. That B, since B is ahead, B emits a crest first, and then A emits the same crest. B emits a crest, then A emits a crest. So B has sort of a head start in time. But typically we wouldn't represent that as a time term. We'd represent it as a phase constant difference. Because the phase constant is really talking about what's going on at the source. Different phase constants mean one of them has sort of a head start on the other.
Okay.
And if we're specifically trying to figure out locations between the towers where there's no signal, what kind of interference are we looking for there?
You said if there's no signal?
Yeah, if we want no signal at all.
Destructive, right?
Yeah, we want destructive interference. That is, we want to find some locations where the two waves completely cancel each other out, so you get no oscillation at all. So to do that, we can use this idea of a phase chart, or not even necessarily the whole chart, but just the idea of the total phase difference. And I'm going to paste in the usual equation we use here. This is ultimately just the equation, the portion inside the sine function from the wave equation. So if you take a look at just what's inside the sine function, let me pull that up. Inside the sine function, we just got this 2 pi t over period plus or minus 2 pi x over wavelength plus phase constant. And if we want the two waves to be destructively interfering or constructively interfering, either way, if we're analyzing interference, what we really care about is the difference between them, the difference in total phase, which could be written as capital phi. Let me pull that up. So total phase is this whole thing, everything inside the sine function. But if what we care about is the difference, like how are the two waves the same total phase or different total phase, let's apply a delta to that whole thing. And we could split out that delta into the individual pieces. So 2 pi t over period. And by the way, it's sometimes an easier way to write that. Dividing by period is the same as multiplying by what?
The frequency?
Yeah, so instead of divided by period, let's call this multiplied by frequency. So 2 pi times frequency times time. And as for plus or minus, these waves are really spreading out in 3 dimensions. As it spreads out from the source, would you say that the distance from the source is increasing or decreasing?
So you said they're emitting outwards.
Mm-hmm.
And they're getting farther apart, right?
Yeah, and if you just consider one source and waves coming out of that source, the wave is getting further and further from the source as it travels. We can consider that the positive direction since it's increasing its distance from the source. And so should we use plus or minus in the equation here?
This minus.
Yeah. In general, for 2 or 3 dimensional waves that are spreading out from a source, we would always use minus here because it's moving away from the source. It's increasing its distance. So 2 pi times frequency times time minus 2 pi times path length divided by wavelength plus the phase constant. But we don't really care what the total phase is. We care about the difference in total phase between wave A and wave B. If we distribute that delta, we get, let's copy this. We can distribute the delta E to each term individually. So delta, the first thing, minus delta, this second thing, plus delta phase constant. Also, what can you do with a constant multiplier inside a delta?
You can take it out.
Yeah. And 2 pi, of course, is a constant, so we can pull out the 2 pi. So we end up with 2 pi times the difference in frequency times time, minus 2 pi times the difference in well, x is really the path length, how far the wave has traveled, divided by wavelength, plus any difference in phase constant, which we know here. We know the phase constant, so we can fill in the difference in phase constant. And let's say you're standing somewhere in between here. Let's say you're standing at some in-between location. We don't know where, so let's just say right here. So here's your location, and we're talking about waves from both of these towers approaching your location. So this wave and this radio wave. If we want to consider the differences between these two waves, what do we know about their frequencies?
They're identical. They're the same.
Right. They both got the same frequency. And in fact, we know what that is. Frequency is 3.75 times 10 to the 4th hertz. And also, what do we know about what time they reach your location? Like wave A reaches your location, wave B reaches your location at different times or at the same time?
Same time, right?
Yeah, you're receiving both of these waves at the same time. We can certainly say wave B has a head start in the sense that it creates a crest before wave A does, but we're going to take that into account as a phase shift difference in little phi rather than difference in time. The important thing is they both reach your location at the same time, so T is the same for both. What does that tell you about delta F times T?
That the change is 0.
Right, there's no difference. Delta F times T is 0. In fact, the only time this term would even be relevant, what would be the only situation where this term is not going to be 0?
If their frequencies are different.
Right. That term only really matters if the waves have different frequencies. And in that case, that term becomes the most important term, because if this term is non-zero, it's a term with time in it, which means it changes as time passes. In other words, if the frequencies of the two waves are different, you get a type of interference that changes as time passes. And what do we call that phenomenon? If you're changing between constructive and destructive as time passes because the frequencies are different.
Beats?
Exactly. This is beats. So the whole idea of beats is a specific type of interference you get if the frequencies are different. So if the frequencies are different, you get beats as the specific type of interference. And then that means that term is the only part that you really care about, because the other terms don't change as time passes. What we really care about is the one term that does change as time passes, if there is such a term. And in that case, you'd use the usual idea of carrier frequency and beat frequency to analyze this situation instead. But in a situation where the frequencies are the same, then this term is just going to be 0. So we look at the other terms instead. For path length, the two waves can definitely be traveling different distances. The distance traveled is what X is all about. So we have XA is the path length, the path length traveled by wave A on its way to your location. And then XB is the path length traveled by the other wave on its way to your location, as measured from the source. So those could definitely be different X values, really depending on where you're standing. What do we know about the wavelengths though?
I remember this from the last video. If you have the same frequency, you're going to have the same wavelength because they're related to the velocity equation. Exactly. And since these waves are both radio waves in air, they're both going to be traveling at the same speed. Same type of wave, same medium. So they've got the same speed and same frequency.
So they're going to have the same wavelength as each other as well. Same wavelength. And we can even calculate what that wavelength is. How could we relate the wavelength to the frequency? How are wavelength and frequency related to each other?
V equals wavelength times frequency.
Yeah, wavelength times frequency equals the speed of the wave. And we know the frequency here, so we can just divide both sides by frequency to find the wavelength. Wavelength equals speed over frequency. And what's the speed of the wave here? What kind of wave is this?
It's a destructive, or that's the interference, sorry.
Yeah, well, the interference we want is destructive, but what kind of waves are these antennas emitting? Yeah, these are radio waves. And radio is actually a form of light. Radio waves, microwaves, gamma rays, X-rays are all just different wavelengths of light, or different groupings of wavelengths. You've got a certain range of wavelengths that is visible light, the colors we can actually see. And then beyond that, in one direction, you've got ultraviolet. Beyond that, in another direction, you've got infrared, wavelengths outside what we can actually see. And then further beyond that, in either direction, you've got X-rays or gamma rays or radio waves or microwaves. Those are all just different wavelengths of light beyond the colors we can see. However, since they're all just light, they all travel with the same speed. Anyone happen to know what the speed of light is?
Is it 340 meters per second?
That's the speed of sound, but light travels a lot faster than that. You can typically see something long before you hear it if it's happening far away. Light speed is, the speed of light is usually written as c. It's a universal constant. And it's about 300 million meters per second, or 3 times 10 to the 8th meters per second. So ludicrously fast. So fast that it took us a long time historically before we even realized light does travel rather than just instantly getting to its location. So it does take light time to travel, but a very short amount of time because it travels so fast. But this is the universal speed of light. Traveling through a material does slow it down. Like light traveling in water travels only about, I think, half this fast or 2/3 this fast or something. But light traveling in air travels almost as fast. Formally, this is the speed of light traveling in vacuum, empty space, but light traveling in air travels almost as fast. So we'll use this as the speed of the radio waves, or the speed of any form of light we care to look at. We know the speed then is this 3 times 10 to the 8th. And then the frequency was given as 3.75 times 10 to the 4th. 3.75 times 10 to the 4th. Hertz is the same as just 1/seconds, so I'll write it like that, cycles per second. And we can reduce this. First of all, the 10 to a power. What's 10 to the 8th divided by 10 to the 4th? Yeah, we can just subtract the exponents, 8 minus 4, we're left with times 10 to the 4th. Meters per second divided by inverse seconds, the seconds cancel out, so we just get meters. And then 3/3.75, that's what? 12/4 over 15/4, so 12/15 is 4/5. I think that's just 0.8, right? So 0.8 times 10 to the 4th, or 8,000 meters. So that would be the wavelength, 8,000 meters or 8 kilometers. So a very long wavelength, which is typical for radio waves. Radio waves tend to have very long wavelength. So that's our wavelength, 8,000 meters or 8 kilometers, if we want to describe it in units of kilometers. Any questions on the wavelength so far? And we'll use that in the calculations later on. But most importantly for the moment, lambda is a constant. Lambda is the same for both waves. And if lambda is the same for both waves, what can we do with this divided by lambda?
take it out.
Yeah.
Yeah.
Since lambda is a constant, the divided by lambda can be extracted from the delta. So we really just get 2 pi times delta x, the difference in path length, divided by wavelength. So that sums up as we know, the time term is gone. And we can just skip to this. In general, if you know that the two waves have the same frequency and therefore the same wavelength, same frequency means the time term just drops out completely. Same wavelength means you can pull the wavelength, the lambda, out of the delta. So you can think of the delta total phase as abbreviated as -2 pi times difference in path length divided by wavelength plus difference in phase shift if there is one. Any questions on that so far? And we know the wavelength is 8,000 meters. We also know the difference in phase constant, pi over 2 versus 0. But we got to be careful here. We need to be, since we've got two deltas in the equation, we've got to make sure we're consistent about that. We need to make sure we're subtracting in the same order. So for consistency, do you want to subtract a minus b or b minus a? We could do either one. We just need to pick an order.
I would say b minus a, but I don't know if that's right.
So let's say delta is a value at b minus a value at a. I'll just make a note of that. So as a reminder to ourselves, and it's also a good idea as a reminder to anybody who's reading or greeting it later. So in this entire problem, we're going to use a value of b minus a value of a for the delta. So delta phi, b minus a, that'll be pi over 2 minus 0. So that's plus pi over 2 minus 0 is just pi over 2. As for delta x, we're going to subtract xb minus xa. So we'll have -2 pi times xb minus xa divided by wavelength. And now we just need to figure out how to deal with xb and xa, because we know the wavelength, 8,000 meters. What do we know about xb and xa? Do we know anything about how those two distances relate to each other?
I was gonna say that since it says you're lost in like the middle of the desert, does that mean like technically you're at 4 kilometers? So
I don't think I don't think we're supposed to imply that to mean
okay.
In the middle, but somewhere in between. But yeah, they've got to add up to the 8 kilometers total, right? We can say however far wave A travels and however far wave B travels, those two distances together have to add up to the total distance between the towers, 8 kilometers. And note this is only true if you're in between the towers. If you're somewhere else, like if you leave this region and go over here, now XA is going to be this distance, and XB would be this distance. So this model kind of falls apart if you leave the region between the towers, and you'd have to set up the math for that separately. But as long as we assume you're in the in-between region, we can say XA plus XB has to add up to the total distance, 8 kilometers. Actually, we could go either way here. Do you want to use meters or kilometers for this?
I have a quick question. So since their frequency is the same, and that means their wavelengths are the same, well, frequency the same, wavelengths are the same, doesn't it mean that delta 2 pi x over lambda term is 0?
No, because the x's are different. The x is the path length, the distance traveled by the wave. Okay. And XA and XB are not traveling the same distance unless you're exactly in the middle at 4 kilometers.
Oh, okay. We aren't given.
Right. We're trying to find where should you stand to make this happen a certain way. However, since the lambdas are the same, we can pull the divided by lambda out of the delta. Since
I see. Okay. Okay. Thank you.
If the lambdas weren't the same, then we'd have to leave the lambda in the delta. So delta x over lambda. But again, in that case, the frequencies would be different, which means that this is really a beats problem, and that's the most important part.
Okay, thank you.
Mm-hmm. So for XB and XA, if we know XA plus XB has to equal 8 kilometers, what would you get if you isolated, let's say, XB here?
Eight minus XA.
Yeah, 8 kilometers minus XA. So we can reduce this, even though we've got two unknowns, distance from tower A to your location and distance from tower B to your location. We can combine those using this fact that they have to add up to 8. Everywhere we see XB, we can replace it with 8 kilometers minus XA. So let's do that. Negative 2 pi times XB is the same as 8 kilometers minus XA. And then we also have a minus XA. Then divided by lambda and plus 2 pi. Also, since we know lambda is 8 kilometers, we may as well fill that in. And now we've got an expression for delta total phase. The difference in total phase between these two waves has to be this expression. And also minus XA, we can combine those as well into just minus 2XA. So now we have an expression relating delta total phase to XA. Any questions on the algebra behind that so far? And now for the actual physics of interference here. We specifically want destructive interference. What has to be true about delta total phase to create destructive interference?
Doesn't the doesn't it have to be like pi out of phase or half a wavelength out of phase?
And if it was just talking about a difference in path length, like if there was no difference in phase shift, if the only difference between these two waves was how far they travel, being exactly half a wavelength out of sync would make it destructive. And I think this might be easier to see if we draw this out. Let's say we have a wave that looks like this. And let's say we've got another wave that's exactly the same, same wavelength. So if these two waves are exactly synchronized with each other, what kind of interference do we have? If we've got crest and crest lining up, trough and trough lining up, crest and crest lining up, what kind of interference would that be?
Yeah. Constructive.
Yeah, that's constructive. The crests combine to an even larger crest, the troughs combine to an even larger trough, so that's constructive interference if there's no difference between the waves. That is, if delta total phase is 0. But if we offset this, let's say we offset this by exactly one whole cycle. If we offset it by exactly one whole cycle, now what kind of interference are we dealing with?
Constructive.
Yeah, one full cycle offset is still constructive. We still have this crest lining up with the next crest, this trough lining up with the next trough. Or if we offset by 2 whole cycles, still constructive, or 3 whole cycles, still constructive. So any whole number of cycles offset is constructive. And what's a whole cycle in radians?
2 pi.
Right. So constructive interference happens when delta total phase is a whole number of cycles. And since one cycle is 2 pi, That means constructive interference requires a whole number multiple of 2 pi. 2 pi times, let's say 2 pi times k, where k is just some whole number. So if the difference in total phase is a whole number multiple of 2 pi, you get constructive interference. You could also rearrange that algebraically a little bit. If you rearrange these and get 2 times k times pi, if you multiply 2 times a whole number, what kind of number do you get?
You get an even, don't you?
Right. So an even number times pi. In general, if the difference in total phase, which could incorporate a difference in path length and possibly also a difference in phase shift, if that total phase difference is an even multiple of pi, like 2 pi, 4 pi, 6 pi, negatives also work. Negative 2 pi, negative 4 pi, negative 6 pi. That counts as a whole number of cycles offset, and a whole number of cycles offset still matches up. So that still counts as constructive interference. To get destructive, you need what fraction of a cycle?
Pi.
It is going to be pi in radians, but what fraction of a cycle is that?
Isn't it pi plus a half? Or a cycle and a half? Or
well, forget about radians for a moment. Just how much of a cycle?
Half.
Yeah, half of a cycle. So in general, if the offset, if the difference in phase is a half a cycle, or 1.5 cycles, or 2.5 cycles, or 3.5 cycles, anytime it's something and a half cycles, then that's going to be destructive interference. So destructive is when delta phase total is something and a half cycles. So not a whole number, but exactly something and a half. Half a cycle or 1.5 cycles or 2.5 cycles. And going back to radians, what would something and a half cycles be in radians?
Like 3 pi over 2.
3 pi over 2 isn't actually something and a half cycles though. 3 pi over 2 would be 3/4 of a cycle. If we want exactly half of a cycle, what's half a cycle in radians?
Pi.
So it could be exactly pi, that's half a cycle. What about 1.5 cycles? What would that be in radians?
3 pi over 2.
3 pi over 2 is 3/4 of the cycle though. If we want exactly 1.5, yeah, that'll be 3 pi. Because remember, 2 pi is one whole cycle. 1.5 cycles would be 1.5 times 2 pi. 1.5 times 2 is 3, so we get 3 pi. And keep in mind, 1 pi is half a rotation. So 1 pi, 2 pi brings you back to the original. The third pi gives you another half cycle. So 3 pi would be 1.5 cycles. What would be 2.5 cycles?
5.
Yeah, 5 pi. And in general, what's the pattern here? What sort of multiples of pi will give you something and a half cycles?
Odd numbers.
Right. Any odd whole number times pi. And notice both of these have to be a whole number times pi. An even whole number times pi will be constructive because that's a whole number of cycles. An odd whole number times pi will be destructive because that's something and a half cycles. But if it's anything else, like if it's something in 3/4 cycles, if it's like 2 pi over 3 or 1 pi over 2 or something, anything that's not exactly an even multiple of pi or exactly an odd multiple of pi, that's neither constructive nor destructive. It's somewhere in between, and we would typically call that partial interference. So partial interference means it's neither one of these, it's somewhere in between. Any questions on that distinction so far?
I do have one question. So if like you're given a problem, I know this is can be kind of vague, but how would you know if their like path length differences are different or the same? Like I know like in one of your videos from last quarter, they gave you that the person was exactly 4 meters away from the other in that one and the total was 8. So there's no difference there. Is it because they aren't giving you like the position where you are? So that's why you can't assume that the distances aren't the same or the same.
Right. Yeah, and this one, I mean, we're really trying to find a location that's going to work. We want to know where should you stand to get no signal.
Oh,
so
so you're
the
solving
location is unknown.
Okay. Okay.
On the other hand, if it specifically said, assume you're standing exactly in the center, then I would assume that XA and XB are the same.
Okay. Okay. I just want to make sure.
Yeah. Yeah, but in this case, since we don't know where we're standing, so far we might be standing anywhere in this region, we should assume that XA could be any distance between 0 and 8, and XB is going to be 8 minus that distance.
Okay.
In this case, though, we can add in one more piece of information. Since we know we're talking about destructive interference, we can assume that delta total phase is an odd multiple of pi. And there are a few ways you could write that. You could just leave it as odd times pi and then fill in odd values for odd later, like treat the word odd as a variable. Or alternatively, any even number can be always written as 2 times k, 2 times some whole number. How would you write an odd number in general, algebraically?
You would do like 2x plus 1, or in this case, 2k plus 1.
Yeah, because if 2k is guaranteed to be even, 2k plus 1 will change it to an odd number. So we can write any odd number as 2k plus 1, where k is just some arbitrary whole number. But for now, let's just write this as odd times pi. We can fill in odd values later. So delta total phase will replace with odd number times pi. And now we want to figure out what's the value of XA, or what value of XA will work here. So I think the rest is going to be mostly algebra. We want to solve for XA. Before we do, though, what shows up in every single term here? In this equation, what value shows up as a multiplier in every term we've got?
Is it pi?
Yeah, we do have 8 times pi in every term. We could leave that there, but to make the calculations easier and the write out a little easier, let's divide both sides by pi, since pi shows up in every term. So if we divide both sides by pi, this pi cancels out, this pi cancels out, and this pi cancels out, if we're dividing both sides by pi. So we end up with an odd number equals -2 times 8 kilometers minus 2 times XA divided by 8 kilometers plus pi over 2 becomes 1 over 2 when we divide by pi. And then we can simplify this whole thing. We could multiply by 2 and divide by 8. So odd equals -2 times 8 is -16 kilometers. -2 times -2 becomes +4 times XA. And then we're dividing that whole thing by 8 kilometers. And then +1/2, so that'll be just still +1/2. And what else do we still need to do to isolate XA here?
Do we need to divide by 4? I feel like my algebra.
Eventually, yes, but work your way from, like in this mathematical expression, just in terms of order of operations, what's the last thing being done?
Oh, yeah. So, yeah.
Yeah, this +1/2 is the last thing being done. So I would start by subtracting 1/2 from both sides. We get odd minus 1/2. And it's probably best to think of the word odd here as just a variable. You could certainly write it as 2k plus 1, but I would just leave it as odd for now. And then what? What's the next thing we want to get rid of?
You want to multiply by 1/8.
Yeah, well, it's already multiplied by 1/8. So what's the opposite of that?
Oh, sorry, multiply by 8.
Yeah, multiply by 8 kilometers. So 8 kilometers times some odd number minus 1/2. And then what else do we need to get rid of here?
Add 16.
Yeah, we've got a -16 kilometers. So let's add 16 kilometers to both sides. And then at this point, the only thing being done to XA is multiplication by 4. So now we can just divide both sides by 4. So XA is going to be both of these terms divided by 4. We've got 8 kilometers times something divided by 4. That becomes 8 over 4, 2 kilometers times odd minus 1/2 plus 16 kilometers divided by 4 will be 4 kilometers. And we could probably even distribute this to 2 kilometers times odd minus 2 kilometers times 1/2. 2 times 1/2 would be 1 kilometer plus 4 kilometers. Combine like terms, 4 kilometers minus 1 kilometer is 3 kilometers. So ultimately we get XA equals 3 kilometers plus any odd multiple of 2 kilometers. Any questions on the algebra there so far?
Can you move it up just a little bit?
Yeah, I think so.
Just a tiny bit. I think I missed a step.
Is that any better?
Yeah, I have the plus 16, and then you divide by 4. Okay.
Yeah, we're dividing both sides by 4, so 8 becomes 2 and 16 becomes 4.
Okay, 16 becomes 4. Yeah. Okay, so you're multiplying the 2 and then you're adding the 4.
Yeah, I think so.
Okay, I get it. Sorry, I just got lost for a second.
Yeah. Yeah, we did kind of combine some steps in there, but it's all algebra at that point. And now to figure out, because ultimately we just want some locations where we can stand to get no signal from the radio towers. So to do that, we can start just filling in some values for odd and see what we get. So let's try that. If we just make a data table of value of odd and value of XA. So what value could we use for odd here? What would be the easiest odd number to use?
1.
Yeah, if we just fill in 1, XA is going to be 2 kilometers times 1 plus 3. So that'll be 5 kilometers. So 5 kilometers is one of the locations where you can stand that will give you no signal. It all cancels out. What other odd number could we use here?
3.
Yeah, let's try 3. If you fill in 3 for the odd number, 2 kilometers times 3 plus 3 would be what value?
9.
Yeah. But what's the problem with that?
It only goes till 8. The difference between the two towers.
If you stand over at 9 kilometers, you're now outside the region between the towers. And that would actually require a different equation, a different mathematical setup. Because the whole setup we did was assuming that you're somewhere between the towers, which is why XA and XB had to add up to 8 kilometers. If you're somewhere else, we'd have to set that up differently. So we should actually negate this idea. 3 does not work because 9 kilometers is outside the region we're talking about. And if we plug in 5 or 7 or 9, we just get further outside the region. So we can't use larger odd numbers. But we can actually go further in the negative direction. What's the next odd number before 1?
-1?
Yeah, we can use negative odd numbers. If we try -1 as our odd number, you fill in -1 for odd, and what does this become?
Wait.
2 times 1 plus 3?
Is it 1?
Yeah, 1 kilometer. So if you're standing at the 1 kilometer mark, this will also work. If wave 1 travels 1 kilometer and wave 2 travels 7 kilometers, that should do it. And then if we go any further, -3, what do you get if you fill in -3 for the odd number?
You get 3 as well, don't you?
-3. 2 times -3 is -6, plus 3 would be how much?
I feel like I don't know how to do simple math.
It takes some practice. But what is -6 + 3?
-3.
Yeah, there we go. The other one.
And -3 kilometers would mean you're where? What location would that actually represent?
On the left.
Yeah, outside.
Yeah, that's 3 kilometers further back from antenna A. And that's also outside the range we care about. So we would ignore this as well. -3 kilometers doesn't make sense in the sense that it's outside the range we defined when we were setting up the model. And of course, more negative numbers will just lead to further to the left. So it looks like 1 and -1 are the only odd numbers that make this work, which means 5 kilometers and 1 kilometer are the only locations that actually make sense here. So you could stand at the 1 kilometer location or the 5 kilometer location. Those are the only 2 locations in this region that would provide completely destructive interference and therefore no signal. Any questions on that?
Thank you for going through that problem.
Yeah, you're welcome. Try this approach on some other examples. Let me know if there's anything else you'd like to try out next time, and I will see you then.
Thank you so much.
You're welcome.